Hello and welcome to the first day of the last week of my x64 practice series here. I'm going to start off today not looking at a problem, but I want to go through all the assembly we've written so far and touch some things up because we've kind of gotten better as we've been going, and so like stylistically things have evolved. I've learned how to do things correctly that I was doing incorrectly before, and I got some questions answered over the weekend between the last stream and this stream, which will allow me to do a better job at a few things I wasn't sure how to do correctly. So I just want to do a pass through all of the code we've written. It's like 1,000 lines at this point. Wow, it's like 1,500, 1,600 lines of code we've written in assembly. I guess not counting this, yeah, 1,600. This we're going to do some stuff with. So we might also clean this up and try to preserve some of it, as we said we would do last time. So if we get to a problem later, we will do more problems tonight, but we might not. We might just spend all the time on cleaning up existing stuff we have here. And I'm okay if that's what this day turns into. But we'll try to get to a problem, maybe a shorter one later in the evening, after we've done some of this. So let's start with, I want to go through all of the places where I've used jumps. Jump 0 is fine. Jump is fine. Jump equal, jump not 0. Jump below or equal. Comparing I with C. Which one is this? This is in our Fibonacci one, so this is rather recent. We got that one right, I think. All of those look like unsigned integers, and below or equals for unsigned, so that should be good. Jump below equal, jump above. Jump above, okay. New function. Fill factorial table. We have any jumps here? Jump above or equal. Jump, again, just using unsigned, so that's good. Jump not 0, jump 0, jump greater or equal. Okay, so what we're looking at here, if you look at, like here I'm using the instruction jump above or equal, and here I'm using the instruction jump greater than or equal. So what's the difference between above or equal and greater than or equal? Well, above implies unsigned. That's the way the words might sound like they're identical, but the idea in x64, x86, x64, the instructions are set up in such a way that greater thans and less thans are talking about signed comparison, whereas above and below are talking about unsigned comparison. So now I found this one. I want to make sure that that's the right things. I don't think I used any signed integers. And I was not labeling, so I don't know. So we're gonna have to go and like update our notation here a little bit too. So what I started doing was putting types on all these things a little bit later on, which I wasn't doing at first. I'm gonna leave the notes because those are other to-dos we want to look at today. But let's see, that's a U32, that's a U32. And yeah, let's see. And that's a list node pointer. Okay, so all of these are unsigned. So when I do jump greater than or equal, I'm comparing, this just says R14 and R10, so I don't remember what R14 and R10 are. So R14 is like a putter, it looks like. And this is like a one pass last. And so we're checking if putter is greater than or equal to a one pass last. Here we're reading out of the putter. So yeah, these are unsigned because they're both pointer types, right? So this should be jump above or equal. Okay, p times p is greater than or equal to 1 past last. Did I already have something? I better call this putter OPL. Looks like I already had something else called 1 past last. So let's see. P is being read out of this pointer here, which is originally pointing at the same thing as an array.v. So I think that's a U32 because these are nodes of U32s. Yeah, so the array part is an array of U32s. So that means after I have putter equals node array v, this is now a pointer to an unsigned type. So when I dereference it here, it's 32 bytes, so I'm only putting it in the 32, or it's 32 bits, so I'm only putting in the low 32 bits of this register, but it's still unsigned. So when I do a comparison here, I'm squaring the number, comparing it. I want to treat that as an unsigned result, or an unsigned comparison. Okay. Okay, again, pointers are unsigned integers. We don't want to use signed comparison for pointers. Jumping on 0, add jump grid. Okay. Again, these are pointer comparisons, so unsigned. Jump less than. These are also pointer comparisons, so there should be jump below. All right, let's make sure our prime sieve is still working. So how do I call my prime sieve? Arena, list of primes, first, 1 past last. Okay, the first should be 3. And we want a list right here. I'm supposed to be able to call this like a couple times like this and grow the list. And then I want to iterate the list like so. Print out that. Okay, so we should get a list of primes that way. Or not. What did we mess up? Oh, I should call that a list. Okay. What do you not like about that? Oh, this is not 64-bit. Okay. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 101, 103. Let's take one of the higher numbers here and just test real quick. Is it prime? Oh, no. Give me the one I like. This one. Yeah, I like this one because it tells you if it has a factor. Okay. So our prime sieve looks good. Let's keep going through the assembly. And that's how we're going to try to proceed here. Modify one function until it looks good, and then test it again. So here we build a factorization table. We put in the types here. Now I need to do a pass to get the sizes correct as well. Okay. BYP64. Yeah, I need to dig into all the answers I got, because I got lots of answers on Twitter and lots of discussion about it that all sound like some of it I've already internalized. It kind of confirmed what I suspected. That question came from. Let me fill in the other folks who might not be following this conversation. So I asked a question on Twitter, or I asked a few questions. Well, one of them was about what happens if you use some memory multiple times in a row. So like if you were to do something like add something to whatever number's on top of the stack like this, and then multiply that by something else like this, and then finally do something like that. What I was curious about was, would the processor have to do a store after this instruction and then wait for that store to complete before this could be done? Or would it be able to see that this is a load from the exact same thing and literally skip going through any caches at all and just use the register renaming tricks? Because I know I'm familiar with the fact that if these weren't RSP, but if they were like R8s, for instance, the compiler doesn't actually, or the processor doesn't actually have to use the R8 register. It uses whatever register it wants, and it has like a big bank of them, and it renames registers. So like it'll look at this and go, okay, I'm gonna take this version of R8 that started with whatever was already in R8, and then I'm going to have a version that has the original value of R8 plus this times this, and I'm going to put that into RAX for the return, and RAX doesn't have to be a real RAX, and so on, right? So it's not the case that this has to complete before some other R8 stuff happens. Like if we were to then move R9 into R8 and then do I don't even know what, but just like anything at all here, right? This could happen at the same time as this, because the processor can see like, this is kind of a totally different R8 because we threw away what was in R8 here. So like this computation is serial and this computation is independent of that. So it then uses two separate internal registers to represent this thing. And since I knew this was possible, I wondered, why wouldn't it do the same thing for memory? And I asked, can it do like, hey, I see that we're accessing the same address in memory multiple times. Wouldn't it just be able to use that register renaming logic to do this as well? So that's what I asked about, and it turns out it can. It's called memory renaming, and it's a really new feature as of like, it's around in some processors as of like 2018, it sounded like. But when it's there, what it means is that this is basically as good as a register. It does at the end have to do a memory store, but until this last line where it's done doing all the work, or maybe it does a store for each one, but none of these have to involve like passing memory back and forth at each operation. This here has to do a load to get the original value of whatever is at that memory, and then it can add something to it and multiply something to it before it has to send it back to memory. It doesn't have to do the amount of time it takes doesn't have to reflect the fact that these were two separate memory accesses, is basically the point. Yeah, so what you're talking about, BYP, is like some older stuff. So store forwarding was another thing that was talked about. So what I just talked about was the answer to my question from someone who knows like super recent stuff that's like, as of 2018, processors now can do this memory renaming thing, it's called. And it basically comes down to, if you use the same, if the processor can detect that the address will be the same, so like in this case, RSP hasn't changed, and so it can detect that they're the same. It turns out it'll even be able to detect if RSP does change, because if you do like RSP or add RSP8, for instance, or so I should say sub. So like if you allocate a little more space on the stack, like I don't know, I'll say like this, for instance. Let me do like this, right? 32 bytes on the stack. It can actually then go like, oh, if you then do this, I'm getting like way out in the weeds here, but like if you then do this, it'll know that like, oh, that's actually the same thing as this from a little bit ago. So it can keep on using that register again and not have to do a memory load. Now, before we had memory renaming, which is the thing we were just talking about, which is basically turning a memory location into almost as good as a register, there is this stuff called store forwarding, which is what the blog post you're referring to talks about. I have to go read the blog post because I'm not familiar with it, but there was also discussion of that online today and yesterday since I asked the question. I think I asked it on Sunday. I can't remember when I asked it, but ever since I asked the question, there's been discussion of store forwarding as well, and I'm not as familiar with what that is, so I won't try to explain it. But from what I understand, it also comes into play in cases like this where you have nearby accesses to memory, but I couldn't tell you what it's about for the most part. Hey, Dan. How's it going? Anyway, let me keep on trying to clean this up. Let's see. Jump greater than or equal to. So that's just going to be wrong. These are unsigned, so that needs to be above or equal. These are going to be unsigned, so above or equal. Jump, jump. Okay, factorization table. Eighth Mage, hello, welcome. So let's ask for 100 slots of the factorization table. How does that get returned to me as an array U32, right? Yeah. So then I just need a loop to go over that. Fact table dot count U32x equals fact table to array vi f printf %u. Okay, let's see if the factorization table looks good. So these are factorizations for every odd number starting from 3. So 3, 5, 7, and then 9 can be factorized by the number 3. 11 and 13 are prime. 12 can be no wait, that's not 12. That's 15 can be factored by 3. 17 and 19 are prime. 21 can be factored by 3. 23, 25 can be factored by 5. 27 can be factored by 3. 29 is prime, 31 is prime. So this looks good to me. The Eighth Mage asks a really good question. Why did you get started with ASM? After writing a big project, I never wanted to do, or after writing a school project, I never wanted to do a big program in it again. So a couple things. One, it's just stuff that I felt like I needed to learn better. I had a class in school too, but it never actually forced me to write x64 assembly. And I program computers that run this machine language all the time. Like I use C and other languages to generate this stuff, but I don't actually know like the details of how it works, or like if I was going to sit down and think about how a particular piece of assembly works or like disassembly works, I just would not really know what I was looking at. So I thought this was just a good way to quickly get a grasp on it, you know? It's a skill I wanted to have. But then there's the other factor that's like, I'd kind of like to start dabbling in writing code generators. I'm not going to, go all the way into all the plans here, but like in the short run, I won't be doing a lot of it, but eventually I've got some ideas of stuff I'd like to do, some like domain specific special case compiler experiment stuff I'd like to play around with, and I just needed to know more about like the ins and outs of this stuff so that I could do a good job of that. And yeah, it was actually a lot of this was inspired by the Dion project, which also involves toying around with how compilers work. And as I was making progress on that project with the Dion team, I started to feel like we needed someone with like a much deeper understanding of this low level stuff, like at this layer. So it's mostly just because I felt like building out knowledge of this layer was going to have a lot of benefits for me on various different things I'm interested in. All right, so the factorization table looked like it was working. Let's keep going here. Jump 0, jump greater than or equal to. I think this is another case where I just think anywhere where I have jump greater than or equal to is going to be wrong. So let's see. I guess I do want to take it one step at a time. Now, let me back that up. Jump above or equal, get prime factor. Okay, so get prime factor. Now, how is get prime factor different from... Oh, because it like handles even numbers and stuff. Okay. So for this one, what I want to do is a loop over all the numbers from 0 to 100. Yeah, that'll be fine. And call get prime factor. I give it my factorization table, I give it the count, and I give it I will start with 1, 2 in this case. And then prime factor divides, let's do it like this, prime factor I. What did we requires right LLU. It's funny, under 100, you don't even get a single 11. We're just throwing a giant table, like a function that just returns a bunch of 2s, 3s, 5s, 7s, and then the only numbers that are larger than that are the prime numbers that don't have any division besides themselves. But it makes sense. Okay, so that gets us prime factors, and that function is still working. Jump greater. Where else did I write that? So let's see. This. Find bounded factors. Okay, I remember this one. So I didn't use variable names here for some reason, but let's take a look. R11 as the min. So this is like move min to R11. Min R11. Min. Yes, 8 mage. 11 times 11 is 121. That's why none of the numbers showed their 11 factor, because my factorization table doesn't include any numbers until the square of that prime. I don't know if you caught the logic behind that. It's kind of interesting that you can build a sieve or a factorization table by skipping to the square of the prime every time you discover a prime, and going from there. Let's see, R11, min R11, whoops, do. 7 max. So I'm just touching up the comments first so that this is like more readable. It's easier to understand what the intent was behind it. Because I just used the register names for all of this, which doesn't actually help. Not sure why I was doing that. Ooh. The genuine sieve of Eratosthenes. Okay. I don't know if I ever... I just now realized that the spelling of that does not at all conform to how I always thought it was pronounced. So I'm not going to take another attempt. But yeah, I'll have to save that recommendation. Sneeze. Nice. So why is R10? What role is it playing? Wait, do I have more here? No, R9 is target product. So let's go look at all the R9s. Target product. R9. Target product. Target product. Target product. This right here is R8, which is max, I think. We just did that, right? Yeah. All right, a little bit at a time here. We're getting there. We're getting there. Let's just take that out of here and put this down here. That's better. Okay, we're gonna do Q R equals, who are we dividing? I'm forgetting. Target product divided by max. If the remainder equals 0, test the remainder. Okay, otherwise, go to too small one, which is sitting right there. Very good. R9, that was the target product. Target product, target product, target product. Do. All right. Min is above max. So there we've actually got to go back through and do the jump fixes now. That's where this started. It looks like I got most of the comments fixed. There's still a target product right there. Target product right there. Jump 0, jump below. Okay. And R10 is like product, right? Target product. Okay, so close now. All right, one last pass to check all these jumps. So jump 0, jump below, jump 0, jump above, jump above, jump above, jump 0, jump. Okay, so that's everything for find bounded factor. So let's see, let's test that real quick. Find bounded factors. Remind me of the signature to that function. A min, a max, and a target, and I get back a pair. Okay. So I want something that's at least 100, no bigger than 999, and has a product of 55,655. What do you got? Does that work? Can you do that? Printf. Result.max. Remind me, how does this actually work? We put into RCX the min and the max. Okay. Okay, what are the A and B? Okay. I didn't find anything. Let's try 99900, because I know that has a solution. Okay. Let's try you know, I guess there's an easy way to generate test cases for this, isn't there? 249999. All right, cool. So that function is still working. So okay, what else we got? GCD Euclidean. Jump less than or equal to should be jump below or equal. And let me also make sure I put in the comments on the types here. So this is a pointer to a pair U64. That's a U64. That's a U64. That's a U64. This here is a pair of U64s, I think. Yep. Yeah, looks good to me. A pair of U64s. So 8th Mage, I have been doing Project Euler problems. I can show you, this is the ones we've done. So I did some skipping around, mostly to knock off ones that were very related to stuff we'd already done. Also to skip a few, like I don't really intend to do this one where you would have to, I'm not interested in doing this one. They want you to add up the number of letters in the English spelling of the numbers, and that mostly comes down to like coming up with all the different casework that like, okay, with the, if it's 100 and it has a single or double digit number after that, then you put an and here, 4 digits unless it's 40, and then it's 5 digits. And you know, I just don't feel like working through all the cases until the answer comes out right. I'm sure it's a good problem for practicing situations where there's lots and lots of casework. But it's not really relevant to what I'm trying to do with assembly. So I skipped stuff like that too. But right now I am doing a pass over all the code we wrote over the other streams to fix mistakes that I have, where I have learned better how to do certain things. Yep, that looks good. So this is an Euler data pointer. This is a string 8 pointer. This is a U8 pointer. The main things I'm fixing are my jumps. Well, I'm going to do another pass to do something else with my jumps, which I didn't realize I was doing the signed version of the comparisons before. So anywhere where I was using signed comparisons where I meant to be doing unsigned, I am going and fixing those. And I'm also just tidying up like the comments I left so that it will still make sense if I look at it again in the future to remind myself of these things. But it looks like this one here, I started doing correct unsigned comparisons above and below instead of less than and greater than. Well, let's keep going. Below, not equal, above, not 0. Jump above, jump above, jump 0, jump 0, jump 0, jump not 0, jump above equal. Yeah, exactly. I was doing lots of jump greater than or equal to's where I meant to be doing jump above, so JAE, jump above or equal to's, and JLE's where I meant to be doing JBE's and so on and so on. But it looks like I've got them all now. And I mean, the trick with that is I was using numbers that happened to be positive in both the signed and unsigned space for all the problems. So like it just didn't show up as a bug, but it totally was a bug and I wanted to go and fix that. So that's fixed, but we still have another round that I want to fix, which is I didn't do all of these the right way. So this is not EDX. I didn't use EDX in this function, did I? No, okay. But then these are supposed to be 32-bit integers, so let's go make sure those are right. So let's start with first and one past last, R8D and R9D. Let's make sure we're doing that correctly everywhere. Okay. So like this right here is a bug because I'm assuming that R8. Well, is that true? Because after a store to this in the 32-bit mode, it should have been cleared to 0. This is still going to be wrong. So let's just throw in like a little extend to 60. Make sure top bits, high bits are zeroed. I believe we can do this by going like this. So this should basically be a way to say I want to make sure that there are zeros in the high bits of these registers. And that's important because they're going to be passed to me as 32-bit integers. So like we could probably generate a bug from this if I took a U64 and pass it to this, because the compiler would then think it could generate code that just passes the register as is, with the high bits being some random garbage. And then this code here, which is supposed to be only considering that as a 32-bit integer, would suddenly be like, hey, look, there are high bits here that aren't 0. I'm going to treat them as if they matter. So this should, since whenever you store to the 32-bit portion of a register, it automatically clears the high bits of that register. So to 0, right? So this should give me the clear to 0 logic that I need. And then this should be okay. So let's do a little bit of Godbolt exploring here. So if we don't need this, if we are looking at something like this and we go, wait, is that why I had that? Yeah. If we're looking at something like this and we go, let me go remind myself what I wanted to do. I'm forgetting. I'm blanking on what the whole thing I wanted to test was. Clear out some space. Thinking. There we go. Should just go with the Godbolt indenter. Let's not fight it. It's probably a waste of time. Oh, it might be sign extended instead of just regular extended. I would have thought that like a bitwise operation would do 0 clear and then like arithmetic operations would do sign extension, but it might just always do sign extension. That's very possible. I need it to clear to 0 the top bits. I think. Well, let's that's what I was going to look at. Okay. So if I am the compiler and I need to clear to 0 the high bits of a 64-bit integer, what do I do? Well, first of all, let's contrive that situation. So uint64t. Let me see. I'm gonna need a uint32t parameter a, and let's have a char pointer putter, and then let's find out what x equals putter plus a. Let's have it return that so that it can't optimize that out. Okay. So it's doing a move to do this. It's saying, let's take the A, which is going to be an ECX with 32 bits. Let's move it to EAX, which will, whatever is here, will just be saying we want to move it to A, but then we'll have it, it'll be 64-bit extend. It'll be zeros in the high bits now. And let me see, I bet if this was already 64 bits, yeah, here, it just adds them together, right? It doesn't have to do anything else. But here, it is forced to first move it into a different register to get that 0 extend. So maybe I should do it that way. So let's see, how do I want to do this? I already have all these registers being used. Do I have any calls in this function? This is prime sieve. Prime sieve does not use any calls. So all of these are just because I need space. So what if I said something like move R8D, or move first and one pass last to R15, R14, and 0 extend, 0 extension. Mob R15D from R8D, R14D from R9D. And now, anywhere where I was using R15, I'm going to use R8. And anywhere where I'm seeing R8, I have to also make sure to switch to R15. So R8 becomes R15. Now it's 64 bits, so we can just do that. R8 is 15. R15 is 8. R8. R8 is 15. R8 is 15. R15 is 8. R15 is 8. R8 is 15. R8 is 15. R10, R12, R13. Okay. Now R14 and R9. Okay, R9 is 14. R9 is 14. R14 is 9. R14 is 9. R14 is 9. R14 is 9. R9. R14 is 9. 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 Okay, there's a very good chance we screwed up on that one. But it looks to me like from the compiler that maybe you couldn't use a simpler trick like just ORing like I was hoping you could. But we know that moves like this zero extend, so we just have to reassign the registers so that they are the right size. Maybe that's the logic. But let's go test our prime sieve again. So we need a list of U32s. We need a list 3100. Two, 3, 5, 7, 11, 13, 17, 19, 23, 29, 39, 97. Cool. I mean, maybe you could. I don't know if you can move something into itself. Let's try it out. Yeah, maybe that works. I guess we need to try something really quick now. I am going to move into RAX. Let's see, we need a number that's like 1, 2, 1, 2, 3, 4 bytes there. So this is on the high part, and then let's OR those together, and then do that. Is the syntax like this? Yeah. Let's go and see this in the debugger. Where is my prime sieve? Prime sieve. This part. Okay, so RAX is some reasonable number, like 0, but then we put that in there. We OR that with R8. R8 is 3, and then it becomes that, and then we do that. Yeah, that looks like it worked. That looks like it worked. Okay, so now we've introduced bugs. So let's undo all the changes we made to this code. So it's back to the original structure. I suppose, okay. Okay. Sieve still looks like it works. And we didn't have to rearrange all that stuff. So that's really cool. Let's go and play with Godbolt for a second. So I bet the reason it moved this to EAX instead of putting it into itself then is because it needs to return this anyway. So it's actually saving a move by not doing that. Yeah, obviously register allocation is by hand is not great. Whenever you need to like rearrange one thing, it causes like a cascade of rearrangements that are kind of annoying. Interestingly, it just won't. Here it's getting that add done with that R9. So you moved ECX and R9, EDX and EAX. I mean, what good did this do you? B. A is our... Oh, but that's a memory read. Ugh. It's so clever. The compiler keeps on avoiding doing that zero extend trick. It keeps on avoiding this. How could I try to force it? You want to help me understand why you won't show me this? B, forgot a comma here. There we go. So yeah, when there's not a lot of free registers sitting around, it does stop avoiding that and uses this move. Ah, that's a good idea. That might be a more elegant way to see this. I suspect it's still gonna do, it's gonna do a change in the register though, right? Like if I do this, it's just going to move it to a different register. I'm trying to get it to use the same register twice. But yeah, we had it using the same register. It needs to not have enough room in its other registers. And it seems like at about a point like that, it gave up on... Here it adds R9 and R8 with that, and it loads it right into a 32-bit integer, and then it proceeds to do 2 adds. So weird. That's fascinating. So it switched to 32 bits early, presumably because it realized that it wouldn't affect the result. Yeah, it's really clever. It keeps figuring out that the low 32 bits won't make any difference. If I switch to a sub, do we see anything different? You can't use LEA then. There's a couple of 4-byte subtracts. And if these are 32 bits, then it can't assume that the high bits are 0. What does that do? It's crazy to me how much it avoids. It's doing a good job. All right. Yeah, that makes sense. If it can do stuff with 32-bit operations, it can encode it in a smaller amount of space. The the one I had did do it. I was able to get it to in place modify it, but I guess if it can do the extension and get more work done in one instruction, it's trying to do that, which makes sense. Anyway, that trick works, and it makes sense. It's not a bad idea. The compiler will do it. So we're going to use that for our solution on these. And now let me just scan through here. Do I have other places where I was not doing this carefully? Yeah, so like right here, same problem. So let's just fix this the easy way. Okay. So let's see, get prime factor. What are the types here? We have a U32 pointer, a U32 count, and a U32N. It looks like I just implemented this whole thing in 4-byte operations, so there's no need to do anything. I didn't have mixed 64-bit, 32-bit logic in this one. So we're good. Four byte. That's 8-byte. That's 8-byte there. So let's see. Okay, I'm already doing these moves, so that'll actually be fine because this will do the 0 extensions that are necessary, and I was already having to do these for some other reason, it looks like. Well, I don't really know what that other reason was. I don't see any sign of me using R10D. What's going on here actually? This isn't totally making sense. So why did I move these out? So that one, did I have a divide? Yeah, so this one was because I needed a divide. R10. Doesn't make so much sense. I'm doing an 8-byte divide here. N divided by F. The remainder is not 0. We go to done. Repeats. We're doing repeated divisions here. And then I'm returning a pair. So this is me returning a pair in RAX. So yeah, moving this into there doesn't make a lot of sense. I could just use... Let me see. There's our 0. I bet I can get away with that for clear to 0. And then that gives me the numerator 64-bit divide. Yeah. 64-bit divide might not even be necessary. I could probably get away with doing that. Yeah, so that'll be 0 in its high bits. That'll put that right thing there. But then I have an issue where that's... Okay, I think I get a concept now. So the weird thing is they said when you do 32-bit operations, it clears the high bits to 0 by default. But a big advantage to that makes it not so weird, is then you can still use 32-bit encodings to get a lot of 64-bit work done in cases like this. So we know that the registers are actually 64 bits, and ultimately we have to deal with that fact. But it's pretty easy to deal with that fact without having to use 64-bit operations everywhere, when we know that we're actually trying to confine the results to those 32 bits. And if it were less bits, if it were 16 bits, then it would be more of a hassle because we would have to manually do all the 0 clears. It does make sense. It does make sense. Okay. That was a tiredness yawn. I might make this a short stream based on how I'm feeling and the fact that, like I said, I may not want to get into a problem after I've done all this. So this might just be our tidy up day, and then we can spend our last day on Thursday getting into one more problem or two. But let's see here. We're getting close to having all this stuff tidied up. Let's go put in some useful comments. The visor count. Okay, so I have to look at RDX here is probably being used. No? EDX. So that's just a pass through from there to there. That's a pass through from there to there. That's a pointer, and that's why it's 8 bits. The rest of the, or 8 bytes. The rest of these are 4 bytes. Yeah, that looks fine. This is an issue. RAX, where did RAX get its value? Looks like it got its value from here. Max divide returns a pair. So I'm doing RAX here. So that's the low 32 bits. R n prime is from RAX shifted right. So this is the high 32 bits that I'm trying to get at. I want to look at how the compiler does that. So suppose I have a struct that looks like this. And I return it from foo. So it's like this. Get it to actually show me though. I'll be surprised if I can find an easy way to do this. A, B, this is like more complicated than what I had in mind. Just gonna inline it. What? Internal server error, what's going on? There we go. All right, it didn't inline it. Yeah, it did. There's no call here. How am I gonna get a chance to see? I can't get it to generate code for something where I don't provide the... No, it does work. Okay, good. So here it's doing the call. But now it can just... All right, so what I have to do is like get it to... Let's do this. P.A, P.B. Can you show me that? Okay, so it gets back a pair U32, which is 64 bits, or a pair of U32 bits. So it's going to try to stuff that into one register without doing any extra work, I think. EAX. Wait, hold on. So let's read the whole thing. It stores, wait a minute. Why isn't it allocating? Why is it doing this? Why didn't it subtract RSP first? Can someone explain that to me? Hey, Nikita, welcome. Why did it? How is it able to do this, where it stored something on the stack without allocating stack space first? And why didn't it just use a push? Like, why is this not doing this trick? Is this the? Can you just do one of these? Like, what is this? But anyways, it's saving RBX, and then later it's restoring RBX. I mean, they're using push right here. Stack red zone. Okay, I'll take a look at that in a minute. But anyways, they're storing RBX, and then they're later restoring it from here. Let's see, here they're doing a shift right on RAX. So they use EAX, shift right, and then EAX again, it looks like. RBX gets the pointer from the first parameter. RDI gets the pointer from the second parameter. So then RBX gets the pointer, gets the final low 32 bits, and RDI gets the high 32 bits. And then they're subtracting 32. Why did they add 32 to the stack? I don't understand that either. Looks like they're not using it. Let's look this up. Stack red zone. The red zone is a fixed sized area in a function's stack frame below for a pushdown stack, the current stack pointer, that is reserved and safe to use. It is most commonly used in leaf functions, functions that don't call other functions, for allocating additional stack memory without moving the stack pointer, which saves an instruction. Whether a red zone is present depends on the calling convention. x86 64 systems use the System v AMD 64 ABI, including Linux and macOS. Use a 128-byte red zone that begins directly under the current value of the stack pointer. Microsoft Windows does not have the concept of a red zone on x86. In fact, the ABI explicitly states that the memory beyond the stack pointer is volatile and may be overwritten by debuggers. However, Microsoft Windows has a red zone of 16 bytes on IA64, 8 bytes on AR, 16. Red zone. Okay, why do we even need to define a red zone? Can I just use my stack for anything? On Windows, the stack grows downward from the high address to low. This is sometimes architecturally defined. Sometimes it is merely convention. The value pointed to by the stack pointer register is the value at the top of the stack. And values deeper on the stack reside at higher addresses. But what's up with the data at address less than the stack pointer? Oh, I see. So this is RSP plus 8, not minus 8. And that's... Wait, no. No, that's still not below... How is this? So if this is the stack pointer, below the stack pointer would mean that you subtract to get to it. But this is RSP plus 8, like it's all stuff already on the stack. Platform conventions for some, but not all architectures define a red zone, which is a region of stack below the stack pointer that's still valid for applications to use. So it varies by architecture. x64, 0 bytes. You sure this is a red zone that we're looking at? ESP minus 4, EX. Save EX below the stack pointer. ECX from the cellular. Read it into ECX. Are they the same? Since there is no red zone on x86, the memory at negative offsets relative to the stack pointer may be overwritten at any time. Therefore, the above sequence is permitted to jump to panic. Interesting. Okay. So yeah, this isn't red zone because it's not RSP minus something, right? It's pushed. It's like at RSP plus 0, there's the return instruction pointer. At RSP plus 8, we're digging into the memory from the previous function calls frame. I mean, technically, so is RIP, but like now we're past the return instruction pointer. They got put on there by a call instruction, and we're just in other memory. You know, this does remind me, I had something else to go check that might actually be relevant. It was an answer to my questions on Handmade Network. So let's see here. There on the top of the stack, function called uses RSP register to know where the top of the stack is. On top of it, RSP is return address. Then there are 4 extra entries for vararg's location. Then RSP plus 28 will be arg5. So when you're trying to get arguments past the first 4, they're on the stack, and according to Martins, they just start at RSP plus 28. So that's another time where you dig into the stack, and you dig past some 4 slots for vararg's locations, at least according to what he's saying here. And it goes, you know, the higher arguments are even deeper into the stack. But that's sort of like saying that there's 4 slots there that are just sort of always reserved. A function's prolog is responsible for allocating stack space for local variables, save registers, stack parameters, and register parameters. Register parameters. I don't know what that means. The parameter area is always at the bottom of the stack, even if allocate is used, so that it will always be adjacent to the return address during any function call. It contains at least 4 entries, but always enough space to hold all the parameters needed by any function that may be called. Note that space is always allocated for the register parameters, even if the parameters themselves are never homed to the stack. A callee is guaranteed that space has been allocated for all its parameters. Home addresses are required for the register arguments so a contiguous area is available and the called function needs to take the address of the argument or an individual argument. This area also provides a convenient place to save register arguments during thunk execution and as a debugging option. For example, it makes the arguments easy to find during debugging. They are stored at their home addresses in the prolog code. Even if the called function has fewer than 4 parameters, these 4 stack locations are effectively owned by the called function and may be used by the called function for other purposes besides saving parameter register values. Thus, the caller may not save information in this region of stack across a function call. Okay, so I think that answered my question. Martin said there's a picture on here that's worth seeing. So caller return address. And then, yeah, okay, so the 4 registers in the ABI, RCX, RDX, R8, and R9, which give me my first 4 parameters, are also allocated on the stack. They just aren't necessarily written to the stack, which seems goofy, but it's saying that the reason for that is to guarantee that there is a standard way to get the address of a vararg's parameter. So that if your very first parameter happens to be the only one that has an address, or the only one that isn't the varargs itself, then you have an address where to grab that spot on the stack, and then the varargs start from there. And then, let me think. And then it said up here that the the space can be used by the call e for anything. So we're guaranteed by the ABI that the space is there, but not that it contains the values of our first four parameters, if we even have four. Even if we don't have four parameters, these are always there. And then, okay, that explains something else too. So then if we want to, we can use that to put RCX there, or we can use it for anything else. So what this is doing here is just using the space that it knows is already there for backing up RBX, probably for the reason that was recommended or suggested by pseudonym 73, which is that this means it can preemptively finish restoring RBX right here and get that scheduled early before the rest of the stack stuff happens. That would make sense. Okay, so that's what you're talking about, the shadow stack. That's what we're talking about. Yeah, and then the other question I had was, why is it bothering to subtract 4 bytes here? Or 32 bytes? Why is it bothering to subtract 32 bytes here, or 4 slots here? And the answer is because it's doing a function call. So anytime we do a call, we need to have 4 extra slots on the stack that we just don't touch. And we have to allow that to be volatile so that the function can do whatever they want with it, which we have not been doing. So let's put that on our to-do list of things to clean up. Okay. So the thing I meant to figure out, I have an answer to, which is that the compiler doesn't have anything cleverer than I do about how to deal with packed return. So when a return value is a 64-bit value that is actually two 32-bit values, it doesn't have any clever way of handling it besides doing the shift and that's all it's got. So wherever I was, I think I was on max divide, or I was on something that was calling max divide, actually. Yeah, so after I call max divide, RAX has the R and the N prime being the high part. And so I just have to shift the RAX register, and then I use EAX both times, is the way the compiler did it. Okay. So which function was that? Divisor count. So let's get some divisor counts in here. The divisor count, what parameters does it need? It needs a factorization table. So give me 1,000 slots of a factorization table. Give me a for loop. Divisor count. Nate's call does that for you. In fact, it would have to. If you could call, you need if you're gonna have like a stack system, you kind of need the call instruction to be a combined jump and save the return all at once. If you had to save the return yourself, you'd always have to do like move like to, I don't know what it would be, RSP the rip value, and then that would have to be the rip value plus however much here. So you'd need like get prime factor R, and so it's like, actually I want to move that there, right? It would be this huge tedious thing. Ooh, interesting. Jump and link. Jump. I see. Yeah, so it seems to me like you could probably make an architecture where you just did jumps and you like figured out with some tricks like this how to actually manage it all yourself. But it like definitely helps tidy things up a lot if you get some kind of help that combines the jumping with the managing the RIP, because when you do the jump it destroys your RIP, so you have to manage it ahead before the jump. And so you want some kind of jump that like helps out with making function calls convenient, it feels like. Which is what a call is. But it doesn't necessarily have to do the stack work, is what you're saying, right? Pseudonym 73. It can just jump and give you the return instruction value, like the pointer that you need, but you let you manage the stack of how you jump back there. Right, you end up not having to put it on the stack at all. You just leave it in that register, and I suppose you use like a variable jump that says jump back to the thing in this register. Yeah. That makes sense. That makes sense. I suppose you probably don't have a return instruction then either, so you don't have to encode a return instruction. You would just encode a jump instruction that has a variable destination. But you have to somehow, I guess you have to read off the stack, shrink the stack, and then jump. Okay. Anyways, let's see. Divisor count. I think we were still testing that one. So fact table dot v, fact table dot count n. Start from 2. Div count equals. Let's see. Oh, is this function slow? Or is it an infinite loop? Let's try to do that for just small numbers real quick. Whoops. 2, gotta go fix this again. 2, you go away. You go away. Okay, boom. Boom. I have someone sitting there running forever, do I? I think we're good. I think we're good. Run. Okay, so we have some kind of bug where there's an infinite loop in our divisor count now. What did I change about divisor count? I'm not sure. I was changing these. Compare below or equal. So if it's a 1 or a 0 in R12D, move count to EDI. Yep, that's all the same. Max divide. Accumulator times equals R plus 1. Just to be sure, this is still fine, right? Yes, okay. So let's go figure out how I busted this so that it can't actually work correctly anymore. Max divide is definitely an infinite loop. So here we are. ECX has n, which should be oh wait, do I have a call stack? So divisor count. Let's start from the beginning of divisor count. That's the thing that's actually an issue right now. So I want to move RCX so that I can do function calls. So RSI goes right there. RDI gets our count. So there's our pointer and our count. And then R12 gets our n, which is 2. We create an accumulator. We check if our n is less than or equal to 1. It is not. We call get prime factor, which is going to clobber some stuff and put RAX to 2. It actually didn't change anything else. Crazy. Max divide is going to take ECX as R12, our n, and EDX has the result of get prime factor. So we have a prime factor there, which is 2, figures out the result of max divide. Here we get, not an issue. I guess this could be the infinite loop actually right here too. So let's take a look at this. Max divide, we divide by R8, that's a 2. EDX gets cleared to 0. EAX got 2, which is the n. We do the divide, and n turned out to be a 1, remainder of 0. If the remainder is not 0, it is. So we can do 1 divide, and there's my mistake. R10 is getting EAX here, but we're just using ECX as the n now. We got rid of the thing where I move. That's where I lost the thread. So I got rid of the thing right here that was like move n into R10, but I'm still updating n by modifying the R10 register here. So what I meant to do here is change this to be ECX. And I need this also to use ECX now. EAX. Cool. And if I take this back to the loop, boop, we get divisor counts for all these things. I guess you get more divisors if you're not just a power of 2. Powers of 2s don't always have the most divisors in this scheme. Yeah. Yeah. You get more for having a balance of factors. It's kind of cool. Okay. Anyway, so we fix max divide. Did I fix divisor count? R8. It looks kind of fixed. RDX. Factorization table, so that's not in the divisor count function. So there we go. Divisor count is good to go. Let's see. Nothing here would be an issue. in terms of register size. These are all 64-bit, 64-bit. Those are 64-bit registers. Yeah, it's right around there that I was getting fed up with being uncertain about the correct way to handle 32-bit sizes, and so I dedicated myself a little bit more to using 64-bit sizes for everything for a little while. What did I do with RSP here? Gotcha. Yeah, so right here I didn't need to make stack space for RSP because I could just put it in the shadow space. Now I know. Just gonna try to make some of these comments more consistent. Right here, my comment syntax got a lot more stabilized. I figured out what I was doing there stylistically. Okay, so there we go. Now we need to deal with this. Anywhere where I wrote a call instruction, I did it wrong. So let's go fix that. Okay, so here, yeah, I'm gonna need to do 64 bits, or 64 bytes instead of 32 bytes. I still need 32 for this stuff, but I want all of this to now get shifted in by 32. So there's gonna be 32, 40, 48, 56, right? That is important because we need to leave 32 bytes there so that we can do call instructions. Now this call has 32 bytes of shadow space. This call has 32 bytes of shadow space. So let me make sure that all the times that I'm using RSP to get to A and S, I'm doing it the right way. So instead of this, I need RSP plus 32. That puts A there and 48. That's got to be 48. Now plus 8 is got to be 30 more, so that's plus 40. top RSI return, right. So finally, instead of this, we could use the existing shadow space. So let's try that. Keyword putter, RSP plus 8, RSI. So instead of pushing RSI, we will move it to RSP plus 8. And instead of popping RSI, we will move it from RSP plus 8. Okay, Fibonacci number. Let's go test that one. Okay, that looks good. Suppose I could do one other thing just for soundness of mind here, which is I want to see the Fibonacci numbers too, so I'm not just getting like 0 for every result. Yeah, that looks right. Okay, so we got more call instructions. Fibonacci sigma, cool. You need to RSP minus 32 right here. Okay, more call instructions. Okay, divisor count. So this one, we aren't using RSP, so all we have to do is throw in the subtract and the add. And that should be it. More call instructions, GCD Euclidean, LCM Euclidean. So again, let's do add RSP, sub RSP. You can use the shadow space here to save RSI and or store RSI without having to do any pushes and pops. All right, more call instructions. What about this one? All right, here I just need more space, RSP32, add RSP32. So that gives us our shadow space for the multiply and add functions. Mol small. Yeah, all of these managed to work without having to do anything on the stack. They all fit inside of volatile registers, which is cool. Okay. More call instructions. I think I just fixed this one. Yeah, call instructions. Okay, this one's not fixed. 32. Add, okay, so that's got the space it needs. Call instructions, call memo. Yes, better make sure we do this one correctly because we didn't even write that, so we don't know if it, unlike the other ones, which we knew weren't actually gonna fail, this one totally could. All right, call instructions. Sub. Okay. So that should do it. We fixed the call instructions, so that's good. Let's do one more thing and wrap it up, which is if we look right now, let me see, I don't think Fibonacci number will show this. It might, actually. Yeah, so this one will show it. So after it modifies the stack right here, stack unwinding will stop working. All right, so let's go, I'll show you that in the debugger real quick. Normally when we're writing code, we don't have to think about how stack unwinding will work because the compiler actually just handles it for you when it generates your executable. It also generates unwind info from your code. Fibonacci number. So here it knows about main, it knows about I from main, right? Now if I step in and let it modify the stack like this, it's now got the wrong idea. It thinks alloc arena somehow called me, it's still correctly figuring out about arena there, so it got lucky, but it's like the stack is wrong here, right? And it's totally possible. Let's see, let me find another call. So can we get it to go into here? Okay, so when it goes into the mul here, okay, it looks like it keeps on kind of working, but it's still wrong, right? We didn't get called, this did not call this, and then this. So it's somehow getting this wrong idea in the middle there, right? And what that's all about is some bogus unwind logic is being applied, and it just happens to sync back up with the stack eventually, but it's not real. It's not like really working. It got lucky and lined up, but it isn't really working out when it unwinds from Fibonacci number. Let me see if I can come up with another example that could show. We've seen this before, but I'm trying to come up with an example to show right now that like clearly, without having to think too hard, determines whether or not, well, like I need something that acts for me as like an indicator of whether we're getting it correct or not. Let's do divisor count. So we need another fact table. Divisor count, fact table v, fact table count, I, count, There we go. Okay. So now what I want to do is step into divisor count in the assembly. And here, unwinding is working. What happens if I step further? Yeah, so you can just see it just gets totally busted. It has right here, it gets some idea that, again, alloc arena is involved, and it syncs back up. But like after one step right there, it's busted, and it remains busted completely the whole time. But it remains busted the whole time, but it's completely busted prior to that sub 32 that we put in, right? And now it's only partially busted, but it's still busted. So we're gonna go figure out how to tell the assembler to generate the unwind info is the plan. And I'm gonna guess, because we haven't looked at this in a while, but I'm gonna guess that this is gonna be, I might not have this up anymore. Yeah, let's go back from here. I think I can clear out some of these older things. I'm gonna guess it's gonna be somewhere in all of these directives you can give it. Alloc stack, push frame. Yeah, this looks like it. So push reg, save reg, end prologue, alloc stack, push frame. Let's just look at all of this. Set frame. Any of this could be relevant. Yeah, x13 pixels, that's exactly right. The executable file needs to have additional info besides just the executable, and we have to figure out how to tell the assembler how to do that. So it looks like after a push, I need to do a dot push reg so that the assembler knows that I want to generate unwind info corresponding to this instruction that will handle doing the push reg there, and I need to do an end prologue after that. So let's start with that for just this function: push reg RSI, push reg RDI, push reg R12, push reg R13. End prologue. Yeah. It does not show the pops here, but I wonder if the pops need... Here's to specify how a frame function unwinds and is only allowed within the prologue, which extends from the frame declaration to the end prologue directive. These directives do not generate code. They only generate .xdata and pdata. Save reg would be preceded by instructions that actually implement the actions to be unwound. It is good practice to wrap both unwind directives and the code they are meant to unwind in a macro to ensure agreement. Fair enough, but no thanks. Missing frame in proc. Okay. Proc frame. Okay, so I need to say proc frame. It's a little goofy. Okay. So let's see if that is enough or if I'm missing more stuff. Where did divisor count? Can I see that? Thank you. Okay. So if I do the push, it can still unwind now because you see it skipped over the info. That info told it how to unwind. And prologue. But when I subtract the stack pointer there, it's still wrong. So I gotta include that in the info too. How do I tell it about that? Alloc stack generates alloc small or alloc larger specified size. Allows MLC to specify how a frame function unwinds and is only allowed with the prologue. Let's see. Alloc stack 16. Okay, so I just tell it how much I'm allocating. That makes sense. Alloc stack 32. Okay. Do. All right, so now we have unwinding working, and if I come into this function, unwinding keeps working here because I didn't do anything to the stack. So I believe that's something called a leaf function, based on my understanding of how these things work, since it doesn't need unwind info in this particular function because I didn't modify the stack basically. So it can just use the default logic, which is that it assumes the return instruction pointer is the first thing on the stack and that there's nothing else to do besides jump to there to find out where we were gonna go next. So that's good. All right. So if we figured out how to do it, now let's go and put it in place everywhere. So, whoops, right back. Anywhere where I did a push or a sub RSP, I need to do this. So here we go, R15, 14, 13, 12, alloc stack 16, and prologue frame. Push. All right, we did this one. Here we go. Prologue frame. Push. Okay, we're gonna put that there, there, and there, push. So we're gonna do this one differently, and then we're gonna probably have to figure out unwind info for that too, but let's do this one with the new trick we learned. Pop R12. Okay, push. All right, here's one that actually needs a frame. And prologue, 12, 13, 14, push, boom, 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 alloc stack 32, and prologue, 13, 14, 15, RSI. All right, I gotta tell it there's a frame. Seems like a lot of this is not as automated by an assembler as it could easily be, but maybe there's a good reason for that. Like maybe you don't always want to assume that push is tied to unwind info and stuff like that. Like it certainly wouldn't be trivial to say that all times you modify the stack like this are directly gonna behave the same way, because you could have like variably modified stack. wonder. It did say something about save reg. So I think we want to use this whenever I do the trick where I don't push something. So like the R12 case. Yeah, mob RSP. So here we have a frame because we're doing save reg R12. What should offset be though? They don't give an example of how this gets used. Offset. I mean, I feel like it's a little hard to be sure, but like that makes sense. And without that, it would probably still be able to do the unwind to the correct function, but it wouldn't be able to restore R12, which is supposed to be non-volatile. So that would be good for it to know how to do that. And there was another case where we did that, at least one other case at the beginning of a function somewhere. Wasn't there? I might have written it differently somehow. RSP plus 8. Clock. Keyword putter, right. But yeah, like anytime where I do sub RSP, I need to be doing this too. So save reg RSI 8. That's my theory on that one. Let's see, this is alloc stack 64 and prologue. Frame there. So let's see. Mob keyword putter RSP plus 8. Here it is again. Save reg RSI at 8. Alloc stack 32. And prologue, that's a frame. Mob keyword putter RSP. Yep, that looks like all of it. All right, let's just look for some sub RSPs that I might have skipped. There's one, alloc stack 32 and prologue frame. Sub RSP. All right, so here's one. Why am I doing sub RSP 8? What's going on here? No. Okay, we can do better. We know better now. Plus 8. Okay. No stack allocation there. Alrighty. Again, don't need that. Switch to using the shadow space. RSP plus 8. RSP. 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 Oh, these are all fine. These are all fine. That's a problem. Wait, is this function doing calls? Maybe it's not doing any calls. Okay, we have an issue here. Because this was a function that was doing calls, and it was using the stack. And it looks to me like it was using the stack for three slots, maybe? 4 slots. Okay, so it did use 4 slots. So we need to go through all of this and be a little more careful. This should be a 64. Okay, we can do this more efficiently. Mauve, okay, we'll start with Mauve Rax RSP or Rax, that should be RSP plus 32. This is gonna be RSP plus 40 or RAX RSP plus 48. And then we test, we don't need this done check thing. We just do one test, and if that is 0, then all of them were 0, and we jump to finish. Okay. RSP here, we'll switch to load effective address. RSP plus 32. It's right here is RSP plus 56 now. When did we... put something in RSP plus 56 though? Div result. Ah, so the call does that. Okay. Very good. And that's a 64 now. Okay, so I feel like that's one we should test. Deck from U64 by 3. So we want a, let's clear this out. U64 by 3, X. Let's ask for the number. Well, let's start with, let's see, there's million, thousand, million, billion, trillion. That's 1, 2, 3, 4, 5, 6. 12 total zeros. Boom, boom. Let's do mul small so that should give us a number with 24 zeros. And then dec from U64 by 3. Gives us the decimal representation of x. Okay, that looks good to me. Let me double check this one real quick too. Looks like this one was not actually using RSP internally, so it should be good. Dec from U64 by N does not use the stack. Okay. This one uses sub RSP, so we want to do alloc stack 32 and prolog and there we go. Okay, let me double check I got all the sub RSPs. Got you, 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 got. Okay, we're good. So if I come over here, this will be a fine test. Dec U64 by 3. Can we step into U and see that unwinding works? Dec from U64 ASM. Dun, 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 dun. All right, so we're just inside our function here, and unwinding is still working as usual. Awesome. Awesome, awesome. Let's see, maybe we run to that function call there, step in. So now we have multiple stages of unwinding. We have the div function. We have dec from U64 by 3. And all the way back to here. Okay. All right, so I think we have done a good job of cleaning up all the code we've created. It's probably a good stopping spot for me. I don't feel like I've got enough energy in the battery tonight to start up on a problem, but we can definitely do that next time. To wrap up strong, but I wanted to before I release this code for other people to look at it, make sure it was not having any egregiously bad patterns in it, and I think that was a good idea to do a pass over that to fix all that stuff. We also just blew it out another 100 lines of code, so it was a lot of work actually that we did tonight. Anyways, anyone who came to hang out and watch a slightly different version of this x64 stuff, thank you. I'll be back again on Thursday to wrap up this month of x64 practicing. We'll see you around. Bye-bye.